I'm Sean Parent, for anybody who wasn't at my previous talk. I'm a principal scientist at Adobe. I've had a number of roles there. I've been at Adobe now about 22 years, depending on how you count, because I was there 15 years, and then I went to Google for about a year, and then back to Adobe. I started my career at Adobe on the Photoshop team, and later I ran Adobe Software Technology Lab. That was a research group that spun out of our Advanced Technology group. I ran that group for about 8 years, and now I'm actually back working with the Photoshop team again. So I've had a number of roles. Turn on my clicker here. So I mentioned this before. A few years back, I gave a talk at Going Native Conference called C++ Seasoning, and it was well received, and I got a lot of requests to write a book. And so since then, whenever I get asked to give a talk, I try to flesh out a chapter of the book. So this is kind of my working outlines. You see, for each chapter here, I've got a goal. Most of the goals, I need to redo the first one because now that one's also stated in the negative, or stated as a negative as far as they're what not to do. And there's a reason there. The word goal was chosen very carefully because what I talk about is not prescriptive things. They're not rules, they're things to strive for, but they can be difficult, especially when you're dealing with a large system, to achieve these goals. So they're not rules, they're not guidelines, they're not things that should be held up in a code review where people said, Sean said don't do that. What Sean said is think about that really hard. And the other reason why they're stated as a negative is because I can't give you all the answers as to what the alternatives are. So these are things to try to avoid, and I'll talk some about better in different ways, but sometimes it just requires more thought. So these are all tend to be open-ended problems. So today we're talking about concurrency. All right. Some common themes in all my talks are that they're all about managing relationships, and what I mean about that is relationships between components and software. Understanding the fundamentals, which I think is incredibly important, learning how to write simple code, and learning how to reason about code through local and equational reasoning, right? So local reasoning means that just looking at a piece of code, you can reason about it without having to understand the whole system. And equational reasoning means that you can describe what something is in terms of something else. A is equal to B, right? A plus B is equal to C, right? So you're able to go through those transformations. Now, this talk started because I was working on what became this product right here. This is Lightroom for web, and this is the complete Lightroom rendering engine running inside of the Safari browser with no plugins. Okay, so for people who don't know, Lightroom is a product that Adobe ships that's a professional photography rendering engine, and it's a parametric model, so it's a non-destructive model. You edit your image, and you can come back later and change your edit and readjust it. So to make this work over the web means that we had to have full parity with the desktop rendering engine. Okay, and this is a piece of code now that's a decade old and heavily tuned on the desktop. To give you some idea, this is a woman in the London subway, and as the train was pulling up, I glanced backwards and snapped the photo, and so that's the unedited photo, and that's what it looks like edited. So this was a big problem, taking a 10-year-old code base that's heavily threaded, getting it to compile with the Emscriptum compiler, which is a compiler that Mozilla puts out that compiles C++ code into JavaScript, removing all of the need for threading in it because in JavaScript you have no threads. You have web workers, which is the equivalent of having separate processes, but you don't have threads. And getting the code to run well and to behave in an interactive fashion. So that was the challenge. So this got me thinking really, really hard about concurrency. And the reason why it got me thinking is because going forward, this code base needs to be shared. So I needed to leave the system in a state where we had a code base that developers could work on that would continue to run and run performant in a heavily multi-threaded environment, and the same code would run very well when you had no threads. Right? So I had to think about what is the actual programming model for how you write threaded code. Okay. So first, some definitions here, right? Concurrency is when tasks start, run, and complete in overlapping time periods, where parallelism is when two or more tasks execute simultaneously, right? So on a single-threaded system, you can have concurrency and you can have threads, and it just means things are time-sliced, okay? But parallelism is when you have multiple cores, right? Or something like a SIMD core, where you can do multiple things at the same time. Now, the reason why we want concurrency is because concurrency is our first building block to enable parallelism, right? If I can't run with multiple threads on a single core, then I certainly can't run with multiple threads with multi-core. The other reason why we want concurrency is because it improves interactivity, right? In the previous thing there, right, when I'm sliding my slider, I'm receiving user events coming in and I'm updating frames. And if every time I update a frame, if that slider stops that the user's sliding, that makes for a pretty crappy user experience, right? So we want to be able to slice things up so that we give good interactivity. Now, goal for this talk is no raw synchronization primitives. So what are raw synchronization primitives? Well, there's these things. They're mutexes, they're atomics. A lot of people don't like me putting atomics on this list, but they're certainly atomics, and I'll explain more about that later. They're things like semaphores, memory fences, and condition variables. Okay? The number one reason why you don't want to use these things is you'll likely get them wrong. How do I know that? Because I've been doing this a very long time and I still get them wrong. Okay. So here is a class that I wrote once upon a time. It's renamed. It's a copy on write class, and it's abbreviated here. It's renamed as bad cow, and the reason why I renamed it is because giving this as an example of a bug, then somebody immediately, when it was just named copy on write, somebody immediately copy and pasted the code from my slides and put it into a working system. So, not actually looking at the rest of my presentation where I showed the bug. So who can find the bug in this code? Right? I'll even help you. The bug is between those two lines. Does anybody see what's wrong here?
Time of check, time of use problem.
It's a time of check and time of use problem, absolutely. Okay? So, and I'm using an atomic here, right? So what happens is I check to see, is my count equal to 1? What a count of 1 would mean is that this object is the sole owner of some shared data. Okay? If this object is the sole owner of some shared data, then I know that it's safe to assign directly into it, right? Okay. If it's not 1, right, then I need to make a copy here. This is my copy on write. Okay? When I make the copy, then I need to decrement the count of this one here. Okay? So what's the problem? The problem is, if I wasn't the sole owner on the first check, then by the time the second check comes around, I might be the sole owner. And if now at that decrement, if I am the sole owner, it's my responsibility to free the shared state. Okay? And I'm not doing that here. Right? So the fix is when I do the decrement, I have to say, oh, okay, when I do this decrement, was I the sole owner and now my count went to 0? And if so, delete the object. Right? So this piece of code shipped in a running system and probably ran for something like 5 years, okay? And it wasn't that bad, right? You have a very short window there where you do that new, where somebody else can release ownership, and if they do, then you'll leak one block, okay? Okay, but it was very vexing because occasionally we would see these blocks leak and couldn't figure out why or where they were coming from. Okay. Even with these slides, I've given this talk now a couple times. I've received 5 email messages where people tell me my fix is wrong. Okay. It is correct. I'm quite convinced. I can write the proof that the fix is correct. The 5 people who wrote to me, all what they believe is a bug, all boils down to one of 2 things in those 5 emails. One is they assume that my bad cow implementation is an atomic type. It is not an atomic type, right? If it were an atomic type, then when I was sole ownership, somebody else could come along and claim ownership of it, okay? So that count could go up. It's not an atomic type in that a copy on write integer is just as thread safe as an integer, right? It just means that I can have separate threads, each with their own instances with shared data, okay? But I can't share a single instance of the cow, right? The cow refers to shared data. The other thing is people don't understand what minus minus x does on an atomic, and that's that it's an equivalent of a fetch subtract, okay, of an atomic fetch subtract, which means the subtraction and the fetch of the value happen as a single atomic operation. And sometimes people think that because I'm doing the minus minus and then my compare, okay, that between the subtraction and the compare, something could go wrong. But nobody caught, I fixed it in the previous slide, that my count was uninitialized. Okay, neither did I. So neither did the compiler, which frosts me. So originally when I wrote the code and it was in a working system, I didn't have this problem, and it's because I wasn't using STD atomics, because the code long predates STD atomics. I was using atomics with different behavior. But an STD atomic of an int, if you just default construct it, right, without giving it any value, is an uninitialized variable, just like an int is. Okay? So I actually introduced a bug, and nobody caught that. Okay? So even atomics can be very difficult to reason about. Why do we want performance through parallelism? Right? This is a slide that one of my colleagues, Russell Williams, on the Photoshop team put together a while ago, but it's very true today. So this is your typical desktop computer, right? And this is looking at where are the MIPS or where are the gigaflops in a desktop computer. Okay, that's the bar, that's the GPU, right? Right? So this is looking at an AMD Radeon, which is a little outdated. That bar these days is getting bigger. If you're running on mobile, it's a little bit smaller. Okay. To get into that, you need to get into OpenGL, OpenCL, CUDA, Direct Compute, C++ AMP, DirectX, Metal, pick your thing. All of those things tend to be C or C++ derived programming environments with constraints tailored towards parallelism. Okay, that's how much of your performance is in the vectorization unit on the machine. Okay, so to get to that, you're going to have to be writing with auto vectorization, or like the Intel compiler will do some degree of that, but you have to know how to structure your code to utilize it. OpenCL can target it, or you're writing with intrinsics, which is where most people end up. If you want to unlock multi-core, as of C++ 11, we actually at least have a threading model there. That's how much of your processor is tied up with multi-core. And if you're talking about just one core, the scalar unit, that's the slice right there. That's what most people think of as straight C++. And if you're writing in JavaScript or Java or something else, divide that by a factor of 2 to 5 these days. Okay? So that red line at the end there is 0.025% of the performance of your machine. Okay? Now this is Amdahls Law. Kevlin mentioned this in his last talk, if you were in here. What Amdahls Law says is basically if some amount of your machine is serialized, okay, then you cannot exceed that in overall performance by adding parallelism. Okay? So in this graph here, you can see if the purple line is at 90%. So if just 10% of our app is serialized, we can never perform better than 10x increase in performance, because now that will be the bottleneck, is that serialized piece. Okay. But the interesting thing about this graph is that you don't hit something approximating that 10x speed up until you get out to 1,000 cores. Okay. The bottom scale on this thing is logarithmic, where the top scale is linear. And I hate the graph for that reason. I think this is a very misleading graph. Okay. So, but this is what you'll find on Wikipedia or in most textbooks, is people draw the graph this way, because otherwise you can't really see the shape of the curves. Okay? But the more telling graph is to just look on linear scale down at the axis. So each line here represents just 10% of serialization. So if I just have 10% of my application that's serialized and I'm on 16 cores, I'm only getting a little better than a 6x speed up. Okay? So Amdahls Law sucks, right? It bites us, okay? And serialization doesn't mean locking on Mutex. Serialization can just mean sharing the same memory, right? Or sharing the same address bus for the memory if I don't have a NUMA architecture, okay? Or sharing the same cache line, right? Anything that's shared within the processor starts to bend that curve down, and it bends down rapidly. Any synchronization, an atomic, bends that curve down, okay? Now, most people think about threading, at least most people, coming from kind of a C or C++ background, in this horrible way. They say, I've got this object that I'm sharing, and I got a bunch of threads that are banging on it, and so I'm going to stick a mutex on there, and we're going to keep rotating that around. Okay? That is a horrible, horrible way to think about threading. Don't do that. We don't want to stop. Okay? No stops. Minimize locks. Right? Now, a lot of people that I find when I talk about mutex and I ask them, what is a mutex? Right? Can't give me a good answer. Say, give me an equivalency to a mutex. Right? Give me a mental model for a mutex. I added this section to the talk because somebody who I work with came to me and said, I'm trying to optimize this piece of code where I've got this mutex and I've got this lock over this big block of code, and I've tried to minimize the amount of work I'm doing under the lock to the absolute minimum, and it's still huge. So now I'm trying to optimize the locks, and I'm playing with like adaptive spin locks and stuff. And I'm like, you're thinking about it all wrong. Okay, so let's take a look at a traditional little piece of code here, right? I've got some registry class that I'm going to write, and it's going to be shared, so I want the operations to behave in an atomic fashion. So I'm going to have a set and a get, right, where I can set a key and a value, and it's just going to store it into a map. And because I'm sharing my map, I've got that under my mutex, and I'm going to get it, okay, and so I'm going to lock my mutex and just pull it out at the same time. Okay, So I've got this little piece of code, right? Now, even here, although it looks like I'm doing just a little bit of work under the mutex, right? And I'm using an unordered map, which is a fairly efficient data structure. An unordered map is a hash map. The amount of time it takes me to hash my key depends on the length of the string. So the amount of work that's being done under the locks here is actually fairly unbounded, right? It depends completely on the length of my string. So it's probably typically small, but it could be big. Okay. There's this line in the C++ standard, and you'd find it in a bunch of textbooks, but I pulled it from there because I think, it's a good way to think about it. It can be shown that programs that correctly use mutexes and memory-ordered sequential sorry, I'm drawing a blank. It's a memory barrier. A sequentially consistent memory barrier, and a memory order sequentially consistent memory barrier operations to prevent all data races and use no other synchronization operations behave as if the operations executed by their constituent threads were simply interleaved, with each value computation of an object being taken from the last side effect of that object in that interleaving. This is normally referred to as sequential consistency. So why is this an important sentence? Well, it means that we can always think about mutexes as if we had some set of operations, and those operations are interleaved, right? So we have op, and I messed up the numbers here, so I can have operation 3 repeated multiple times, right? And what an operation is that's the code that's executing under the lock. And it's operating on some value. What's that value? It's the set of all objects that are modified by that operation. Okay, so by all operations. Okay, so X is everything that gets modified within my lock. Okay, by all the pieces of code that acquire that lock on the mutex. Okay, and each of those can yield out some value, some result. Right, those operations it's a read, modify, write operation. They can read, modify, write the data under that, yielding out some result from the read. Okay? So the same is true of all atomic operations, right? So there's really not a lot of difference between an STD atomic. In fact, there's a call on STD atomic that says, is this lock free? So what that means is there processor support to do that as an atomic item within the processor, or is there not processor support, and the compiler has to generate a mutex pair to lock, make the change on the atomic operation, and do the unlock, right? So all that mutexes and locks are a way to construct atomic operations, right? So if you look, fetch subtract follows from my previous example. For the bad cow, you're doing a fetch and subtract. That's a read, modify, write operation on X for the atomic. So what we have here then is that we can take any piece of code that has mutexes and we can transform it into a queued model. Okay? So if we assume that I've got a serial queue, and my serial queue has just one operation on it, which is go async execute this thing, and it's the same calling conventions as STD async here, except it guarantees that the next item being processed in that queue doesn't start until the previous one completed. Okay? Then I can rewrite my set string to go do queue.async. Okay, and I can rewrite my get string, but I've got a little bit of a problem there in that I need the result back out, and I need it paired with that particular get. Okay, so I'm going to use a future there, and we'll talk more about futures. Okay, and I've got the queue async here. Why is this important to understand? Because any place I have a mutex in my code, I can always make this transformation. I can always transform it into a serialized queue model. And that means that within the serialized queue model now, anytime somebody comes along and says set here, regardless of the amount of work that set takes, the time it takes for set to return back to the caller is constant. Okay? So that means that I can add something like set an arbitrary set of values, a whole vector of key value pairs. Okay? And to the caller, that set will take just as much time as the previous set. It's a non-block. Okay? So this puts an upper bound. Now there's overhead in this, right? I've got to queue an item, I've got to dequeue the item, I've got to deal with futures if I've got results coming in. If I'm calling this set as opposed to calling just set string, maybe I have to construct my vector of pairs. I can't just pass iterators in there because my whatever I'm passing iterators into might go away. Okay, so there's overhead in this, but it gives me an upper bound. Okay, so if I'm looking at a piece of code where I'm like, I've got this big frickin' piece of code with a bunch of mutexes around it, I'm like, you're totally in the weeds. Right? So it places an upper bound on both synchronization overhead and time to issue operations. Now, a couple more definitions. Threads. A thread is an execution environment consisting of a stack and processor state running in parallel or concurrent, bugging my slides, to other threads. Okay? A task is a unit of work, often a function that you want to issue on a thread. So tasks are scheduled. They can be scheduled onto a thread pool to optimize machine utilization. Right? Threads tend to be relatively heavyweight because they're carrying around processor state and stacks. And if you saw Kevlin's talk previous to this, he had a great graph showing just how expensive it is to do a task switch from thread to thread. Right? You can do an awful lot of processing on a task switch. Now, unfortunately, C++14 doesn't really have a task system. We have threads, okay, and we have futures, okay, but we don't have a task system. Now, worse, its implementation defined whether or not STD Sink spins up a thread or executes it on a thread pool. In C++11, it was actually defined that it spun up a thread, but Microsoft complained because under Windows 10, Microsoft doesn't want to expose developers to threads. They want everything to go through the Windows thread pool. So they didn't want STD Sink to spin up threads. So in C++14, they changed the standard wording to say, well, it's undefined. Maybe it's a thread, maybe it's executed on a thread pool. We're not going to tell you. And I'm going to show you in a few slides why that was a very problematic decision. Okay. Now I'm going to walk you guys through building a tasking system. We're going to build kind of a portable reference implementation in C++14. But don't do it on your own, right? Not unless you have to. I actually had to do this because in the previous slides, getting Lightroom Web to run, one of the places where I had to make it run was inside the Chrome browser using Pinnacle, which is Google's portable native client. And that's basically an environment where you can run threaded C++ code inside of the browser, so long as it's a Chrome browser or on a Chromebook. But they didn't have a stock tasking system for it, and I couldn't find a reasonable one that was open sourced. Apple's Grand Central Dispatch is open sourced, but it has a lot of dependency on libkernel, and I don't have a kernel inside of Chrome, unfortunately, so I couldn't make that work. But there are lots of good ones here, right? There's Windows has Threadpool and PPL, Apple has Grand Central Dispatch, which can run on Linux and Android. There's Intel TBB, there's HPX. I'm sure that you can find others, but those would be the ones that I would recommend. Okay, this is one that I would not recommend. So there's a little link in the URL there. Oracle has this paper that they published years ago, which is how to write high-performance multi-threaded server code, and as an appendix, they have how to build a tasking system in there for a thread pool. this is their model. You've got a queue, you issue tasks into the queue, the tasks get dequeued by multiple threads. You have one queue per piece of hardware that you have. Their implementation is about 20 pages, but we can build with C++ a better one pretty quickly. So we're going to build a notification queue here. We're just going to build it out of a deck of STD functions with a mutex and a conditional variable around it. We're going to have a pop operation, which is just going to pull one item off of the queue, okay, in our function. We're going to have a push operation to just push one item in the queue and notify anybody who might be waiting on the queue. Okay. And then we can build a tasking system where we have count, which is the number of cores we have, and our vector of threads, okay, and our notification queue, a run function for our threads, which is just going to create a function, pop the function from our queue and execute it. Okay. And then our constructor here for our test system will spin up one thread, binding it with a lambda against our run. When we destruct, we need to join all of our threads. And then we're going to have an async operation where we just take a function and we push it. Okay, so pretty primitive. The one thing, we would hang on destruction right there because we didn't have a way to signal done. So we'll add that real quick. We're going to have a bool that's done. When you call done, we're going to set the bool to true and notify everybody. Okay, in our pop function, when we're waiting, if we get woken up from our condition variable, then we're also going to be checking done, right? Returning false. And that's it. That's the complete thing. So how do you guys think this performs? Right? I already told you, right? Badly. You kind of barely get off the mark. It's horrible. Why is this horrible? It makes a good example, right? It's easy to write. There's nothing fundamentally wrong about it. It's exactly this model, right? We've got a single queue, and we've got a bunch of threads, and they're banging on that queue. Okay, and we've got locks around it. Now, unfortunately here, understanding that I can transform those locks into a queue model doesn't help me, because all I have is a queue with locks around it. Okay, so I need to come up with a better way. Okay, so that sucks. So here's the common answer. I put a queue on each thread that minimizes my contention. Okay? So let's write that. We can do this pretty quickly. We're just going to have a vector of notification queues. We get to reuse our same notification queue. Okay, one for each thread. So now our run is going to take an index into which queue it's actually bound against. When we join now, we need to tell all the queues they're done, not just one. And when we're going to do our push, we're going to keep a little atomic index so we can be pushing from multiple threads. And we're just going to keep incrementing it, but then we're going to modulo it by our count. And so we're just going to round robin, going through, pushing into it there. Okay, and if you notice, that's unsigned, so wrapping around on that index is not a problem. Well-defined behavior on our overflow. Okay, it's a modulo arithmetic. Okay, so how do you guys think we did on our speedometer? Twice as fast? Is it going to go halfway up? Where's it going to go? Nobody? So I actually did profile all this code. I wrote this all, profiled it. It's about 10 times better. Okay? Barely gets us moving. Okay. So, and we have two problems here. One is is I can get a long-running task in one of my queues, and it can cause a bubble, and I can have my other cores sitting there idle. Okay. So the other is even in a fully loaded system, I can end up with a fair amount of contention, right, where one of those mutexes blocks, and that's, you know, upwards of 1 million cycles to do a full task switch, right, in overhead. So hitting one of those mutexes and actually having it locked kills performance. Okay. So here's the next solution, right? It's called task stealing. Okay. Now, there are lots of sophisticated algorithms that are heavily tuned for doing task stealing, but we're just going to code it very simply here. And the idea with task stealing is if your queue, you being a thread, is busy because somebody's pushing in the other end, okay, or it's empty, either you don't really care, see if you can go pull something out of somebody else's queue. Okay? So let's do that. So we're going to take our pop and we're going to have try pop here. Okay? So our try pop is going to take a try lock on our mutex. Okay? So it's going to try to lock. We'll either get the lock or not. If we don't get the lock, we just return false. Okay? Or if the queue is empty, we return false. Either way. Okay? So we'll do that. We're going to do the same thing on our push, just for good measure. Okay? So if I'm trying to push something into a queue and that queue is busy, I shouldn't wait on it. Okay? Hold a mutex, cause a whole processor task switch, even do a spin lock. Okay? What I'm going to do is, if it's busy, I'm just going to return false. Okay? Couldn't push it. Okay? So now our task system, our constructor and destructor stay the same. Okay? But when we do the run now, what we're going to do is we're going to do try pop, and we'll just run once around all the queues. Okay? And then if we don't get anything once around, then we'll just wait where we were. Okay? Now, on the push side, we'll spin around, and it turns out on the push, if all the queues are busy, right, you have to push. Okay? So what are you going to do? Well, you could just sit and wait on one queue, but there's no guarantee that that's the first queue that frees up. Okay? So it's actually better on the push to spin a little more. Okay? So I've got a K there, right? And there's a trade-off there. You're improving overall throughput of the system versus sacrificing a single core to burn it in a spin loop. So whether or not it's a win in your system depends on what the load is on your system. Okay, whether or not you have that core to burn. So, but you can tune it quite a bit. So now how do you think we did? Okay, so way better. Okay, so we got way up into there. Now, at this point, we're about 100 times better than where we started from Oracle's example code. So this is a pretty huge improvement. Okay. Now, what I was benchmarking these at was Apple's Grand Central Dispatch. That's my 1.0, right? That's my full thing. Apple's Grand Central Dispatch is a very nice piece of work if you actually go and read the code. And it even has hooks into libkernel, and the reason why it has hooks into libkernel is because it understands when one task is blocked and how to go just ignore that task and go take care of other things. So you cannot match it with the primitives that you have in standard C++. Okay, but we actually came within about 15%. okay, of it with some straightforward code. So that's pretty good. Okay. Now, if you happen to have libdispatch, this is a standard STD Async compatible function. I'm not going to walk through the whole thing here. That sits on top of dispatch async f, which is a call into libdispatch. So this is fully STD async compliant, including allowing you to move arguments through the whole thing and stuff, written in terms of dispatch async. So if you're on a machine where you can use libdispatch, by all means, steal this code and do. Okay. Now, the first time I gave this talk, somebody went and bent my ear for about 3 hours and said, well, if you're doing anything, you should be writing it in terms of ASIO and ASIO tasks, because that's been proposed to the standard, and ASIO being asynchronous I/O, and it has been as an experimental library. And I think ASIO is a beautiful piece of work, so don't get me wrong here. But ASIO is not a tasking system. So in fact, ASIO doesn't even have tasking primitives. So as this person's bending my ear saying, why didn't I use ASIO? I'm like, well, what are you even talking about? Okay, but you can build a tasking system out of ASIO, and this is what it looks like. It's fairly straightforward, and that's how it performs, almost identically to my first piece of code for exactly the same reasons. In here we have a single service queue that we are posting work to, and it's under heavy contention, and it's getting pounded upon. It is actually slightly faster by about 10% than my implementation with a single queue, okay? But that doesn't show up as a pixel even on my speedometer. So that's where ASIO is. So don't let people tell you ASIO is a tasking system. It's not. Okay, so now we have a system where we can issue tasks. So what happens? We issue a task, which is some function, some work bound to it. It goes and executes. We've got another task. That task yielded some object, and we want to communicate that result to something else that's executing, right? How do we do that? What's our form of communication between tasks? Right? Well, this is where futures come into play. Okay? So we're going to calculate Fibonacci of 1,000,000. CPP int is a boost infinite precision math type. So that's an infinite precision integer. Okay, anybody have any idea of how big Fibonacci of 1,000,000 is? So it's big. Fibonacci is often used as an example in parallel algorithms. Please stop. Almost every talk I go to on parallelism uses Fibonacci numbers. Here's why. So there's a slow way to calculate Fibonacci, which is what most people demonstrate, and there's the proper way to calculate Fibonacci. To calculate Fibonacci, what you need is a power function. So this power function will take x to the power of n for some operation. So if my operation here is addition, then this does multiplication. Okay? If my operation is multiplication, then this does exponentiation. Okay? So this is a generic form of it. Unfortunately, power isn't in the standard library, but it should be. If you want more information about how this works, there's a great write-up on it in Alex Stepanoff and Dan Rose's book, From Mathematics to Generic Programming, kind of the full history of this algorithm. It's also known as Egyptian multiplication or the Russian peasant algorithm. Okay, so what I want to do then is I want to take a particular matrix, which, there it is. I want to take that matrix, which is 1, 1, 1, 0. Which is known as the Fibonacci matrix, and I want to raise it to the, let me back up. Didn't mean to go that far. That's Fibonacci of 1,000,000. Yeah, that's why my clicker is slow. Okay. So I want to take a Fibonacci matrix, raise it to the nth power, and that will give me the Fibonacci number of n plus 1 in the top left, Fibonacci n on the two diagonals, and n minus 1 in the bottom right. Okay, so I can actually take Fibonacci here of n minus 1 and pull Fibonacci n from the top left. Okay? So, with that code, and now you see the delay here. It takes Keynote a minute to prep this. This is the result of Fibonacci of 1,000,000. Okay, it took 0.72 seconds to calculate on my old, not on this laptop, on my old 2013 or so MacBook Pro. It's 208, almost 209,000 digits, and it calculates, and that's just running single-threaded. Okay, so I can calculate way bigger Fibonacci numbers than people do in their parallel examples. The reason why it bugs me is because I've actually seen people use the bad algorithm that people use to demonstrate with parallel algorithms in actual code. Okay, stop. So try to only give real examples. So we'll calculate Fibonacci of 1,000,000 with our future. So what's our mental model of futures? Okay, what we're doing is we're taking a function and we're slicing off the result. Okay, so what I end up with is a function, okay, that still takes some arguments, but has no result, and a future, which is a token for the result, and that future will appear sometime later. Okay, so that's the model of futures. It's separating the function from the result of the function and having a communication channel before them. Now, the nice thing about futures is they allow minimum code transformations to express dependencies. Okay, so if I have a future, and the other nice thing about futures in C++ is they can marshal exceptions, right? So if I have a future and I fail, this will end up printing failure. Right? So across threads, my exception can be thrown in one thread and caught in the other. Okay, so my arguments go there. And then I call future.get, and that's a stop. Right? We just block that thread while we wait for the result with STD futures. And then the result comes over. I hate stops. Right? Unfortunately, C++, even 14, lacks continuations. What's a continuation? Instead of saying .get and stop, you say when the result for this is available, then do the next thing. If you've done JavaScript programming with promises, it's the same idea. Okay? So along with that, C++ 14 lacks joins, which are when all and when any. When all these features are available, do something. It lacks splits, which we'll talk about more, cancellation, and progress monitoring. And C++ 14 features don't compose particularly easily to add these things. Okay, so what's the model for continuations? Well, what we've got is a function yielding a result, which we want to chain to the next function yielding some result, and so on. Okay. Now, STD Future has two additional problems. Okay. So first is that it consumes one resource, right, which we talked about, increasing contention. But it possibly deadlocks if you have a tasking system. And any non-subsequent, non-dependent calculations on the task are also blocked. Now, even though C++ 14 doesn't have the primitives, Boost Futures has .then, with TS Concurrency, which is follow-on to the standard, has .then. TBB has flow graphs. PPL has chain tasks. GCD has serialized queues and groups. These are all things to solve the same problem as continuations. Okay, so how can Git cause a deadlock? Well, let's say I have a task and it issues another task, and then it waits on a get. That other task will never complete because it's not coming out of the queue. So if I'm on a single-threaded system, okay, then a future.get is an immediate deadlock. This is why promises in JavaScript do not have .get or .wait. They only have continuations. In a single-threaded system, it's an immediate deadlock. Okay, well, what if I have two threads? That guy issues two tasks. One task goes into the queue. He waits for it. He's deadlocked. Well, the other task could task steal unless he issues a task and waits for it. And then we're deadlocked. Okay? And so on. Right? It's very difficult to use, future.get is very difficult to use safely in the presence of a thread pool. An STD Sink, it's undefined whether or not it's a thread pool or not. Okay? That's a problem. It's not just get, it's any conditional blocking, right? Such as condition variables, wait, are problematic in a task system. They're exactly the same thing. Right? Somehow I dropped a negative here. This should say, do not call STD Future Get or STD Future Wait when the originating task or any subordinate task is on the same queue, even if it's a concurrent queue or a thread pool. That's the rule for using them safely, okay? Which means that I can issue a task within C++ with async from my main thread and call get on the future, okay? But I can't call get on a future from anything that was queued through STD Async. Okay? So you see this problem in every tasking system. It will have some kind of warning like this. So I could have put a whole list of them up there, but this is from libdispatch, since I've kind of been using libdispatch as an example. You should never call dispatch sync. What's dispatch sync? It's the equivalent of queuing something into the queue and then waiting for it immediately, right? Never call dispatch sync from a task that is executing in the same queue that you are planning to pass to the function. This is particularly important for serial queues, which are guaranteed deadlock, but should also be avoided for concurrent queues. Okay, why? Because depending on how the stars align, it will be a deadlock. Now, how did I discover this? Well, taking a heavily threaded piece of code and taking it down to one thread, it was very apparent where all the deadlocks were, right there. But then we also realized that, hey, if we took it to mobile, where I also took the Lightroom engine to mobile, with 2 cores, we were seeing a lot more deadlocks. Okay, when we actually finally figured out what in the world the problem was, we realized that even on 8 cores and 16 core machines, the system under heavy load would occasionally deadlock. It was just rare enough that you wouldn't see it. Okay, but in our bug backlog, when we went back through, it was like, oh yeah, this is that problem. This deadlock is that problem. Okay, so huge thing. Okay. So this is what a dot then continuation looks like, right? We can calculate Fibonacci, and then once the Fibonacci gets, we can serialize it. Okay, now we're going to go ahead and put our wait in here because we're executing this on the main thread, not over on our async. It's useful at least for debugging. So now we can do it and then print it. Okay? So thens are the equivalent of completion handlers. Okay, and in the standard committee, a lot of times there's debate over whether or not the futures are the right model or whether or not completion handlers are the right model. Okay, so conceptually the two are interchangeable. Okay, so the advantage with the completion handler is that there's no need to synchronize between invocation and setting it because it was set in advance. The completion handler gets passed into the function. Okay, whereas a future, there's a little bit of synchronization that happens because you don't know while your asynchronous task is setting, when you're setting the value, is somebody attaching a continuation at that exact moment in time. Okay, so there's a small amount of synchronization that has to happen. But the advantage with the future is that you don't have to know where the results are going in advance, right? So those are the trade-offs. So you can actually express one in terms of the other, and vice versa, if you build a system correctly. So my answer is always, when people say, "Do we want futures or completion routines?" I'm like, "Yes, that is my answer." I want both. Okay. Now the other thing you find when you start to construct these things is we need joins. Okay, so what I want to do is I have two futures, and when both of those futures are available, then I want to issue the next task. Now, a lot of people have the wrong mental model about this. What they think is then I will have my continuation, I get one result in, and then I will block and wait for the other result. But that's not how joins work at all. What happens is you keep a count of how many things that you're waiting for that are pending. Okay, and when I get one result in, I issue the task, or when I get one result in, I'm okay. When my count goes to 0, then it's the setting the results, decrementing the count to 0 that causes the next task in the chain to fire. So you're never blocking and waiting. You're just counting down. Okay, so this is what it looks like with this is using boost win all. I really do not like the syntax here, in that a win all, right? I'm taking a win all of two futures and then a continuation, and my argument f coming in there is a tuple, is a future of a tuple to futures, which is why you get in order to print my int, I've got get times get, right? Right, f is a future tuple of futures. And the result of this is a bunch of digits. We're not going to print it. So the other thing you want to be able to do is split. So here, now this is still the boost / proposed C++17 model. So it seems like the way you would do a split is just attach two continuations to your future. So I've got x, and then I want to say, then go multiply it by 2, and also when I have x, divide it by 5. That looks like a split. Yeah, it's a sig abort. Okay. The reason is the first then actually consumes x. So trying to attach a second then is a sig abort. That's not a particularly friendly thing. Now, a shared future lets me copy them around, okay, and do multiple get operations, but it still doesn't let me do multiple then operations. Okay, well, that's horrible. So now if I've got a shared future in my hand, I don't know whether or not I can attach a continuation to it. Okay? So, in my opinion, a future should behave as a regular type. It's a token to the value. So you should be able to copy them to get a split. But in absence of that, we could write a split. So let's see how we would do that. Okay, so this is what it would look like to call. What we're going to do is we're going to take x, we're going to split it, okay, which is going to leave our x as a future and give us a new one to which we can attach our dot then. Okay, so we can split it, and then we can attach it. And if we wanted to keep going, we could keep splitting. Okay, we could just keep splitting x. So, and then we can write this, and that will print that, right? The first one being times 2, and the second one divided by 15. Okay, so let's see how we would build that. Well, first we've been talking about futures, but we haven't been talking about the other end of futures, which in C++ is known as a promise. Okay, so a promise is the sending side of a future. So if we create a promise x, then we can get a future out of it. And if we set the value 42 on our promise, then we will get the value out of our future. Okay, so that's the pairing there. So internally, async, STD async, is creating a promise. that will print our 42. Okay, so here's how we're going to write our split. We'll walk through it here. Okay, when we initially come in, there is a promise somewhere, that's in gray, our gray circle, okay, which is going to set our future, which is x. Okay? So we've got a promise somewhere, and we're hanging on to x. So we're passing in a reference to x. Now the first thing we're going to do is we're going to move that future out of x to get it out of the way. Okay, so the promise still points to the move future now, which is in temp. Then we're going to construct a new future and get a new promise for it and put the new promise into x. Okay, so now we've rewritten x to be our new future. Okay, then what we're going to do is we're going to take our temp, okay, which is our future, we're going to put it in to our lambda here, so now it's underscore temp. Okay. We're going to attach a continuation to it, okay, which is going to return our result. We're binding P, right? We are moving the promise we created in the dotted line there. Okay. So we took P, we moved it over into underscore P. Okay. So that's the result. We have the original promise, which points into our underscore temp future, okay, which has a continuation, which is going to set the value on P, right, underscore P set value, okay, and it's going to return the value, right, so there's the copy right there. So that's how we implement a split. Okay, then we do the same thing to split the exception, right? So we want the exception to also go down both paths. Okay, so if we have an exception, then we're going to send an exception down both paths. And that's how we write a split. Okay, now here's a tough thing. This is something I want with futures, but they're not in the C++ 17, and I don't know of a good way to compose them into the C++ 17 futures. Basically, what I want is now that I can split my futures, right, and I can join them so I can build these complicated graphs, is when the last piece of code, let's see, I think I have a graph here. When the last piece of code lets go of a future, like the top right one there, okay, then if the task associated with that piece of code hasn't started to execute, then I want it to not execute and to free the resources, okay, which then leaves two futures which are no longer needed, and so those futures go away, and I'm left with this, right? So I eliminated one task from my system that's executing. Now, when you're developing interactive software, this comes up a lot. The user does something, and then the user does something else, and you're like, okay, well, forget about that old thing. You don't want to keep doing it. So a cancellation model is nice. Because that wasn't there, and because even the boost futures with continuations will deadlock on a single-threaded system, which I consider a bug. They shouldn't, but they do. It's a part of their implementation. I ended up writing this experimental library, which is available on that website. And I've got futures in there that support multiple continuations, and they can be copied. They're optimized for R values, so you can have move-only types with them. It supports joins for win any and win all. It has cancellation on destruction as well as an explicit reset. And it has a detach, so you can detach a future, meaning that now I can destruct this, but I still want whatever it's associated with to continue processing, right? Just like you would detach a thread and say, keep going, even though I'm destructing my token to hold on to it. So I put this library out there, and I have to thank Felix Petrosini, who's in Germany, who's been just a massive contributor. And so when I wrote it to the extent that I needed it, and to kind of show it to the standard folks and say, here's some issues with the direction you're going. And Felix has really kind of fleshed it out, and our goal now is to release kind of a 1.0 version sometime early this year. That's there. But futures aren't enough, right? So the next thing is to talk about channels. And I am probably way over time, aren't I, at this point? I'm not seeing any hands. Since this took me a little longer to go through than I wanted to, I will stop here. Kevlin's already talked some about the basic concepts of channels. Channels are also in my library, so if you want me to discuss them, just see me outside of this. And the last thing, I will just flip through slides very quickly, that I wanted to finish on. Yeah, this slide won't let me go too quick. All these great animations. Talking about flow control and channels. Is this. What we're building here is dependency graphs within the code. And it turns out there's a lot of information in the graph, right? When you're building channels and you're building futures, you're building dependency graphs. And there's a lot of information that's in the graph. But these are what I call incidental data structures, right? There is no place within your code where it's like, here's my dependency graph, okay? Which makes it nearly impossible to mine that graph for values, especially if you want information about all the possible states of that graph. So maybe constructing these dependency graphs is not the right approach. Instead, maybe we should be actually writing the graph descriptions and compiling those and statically validate them. And I've got a whole body of work and a bunch of published papers on something called property models, which is exactly that, which is how do you describe dependency graphs and flows between states and reason about them outside. So if anybody wants to talk on that, way outside the scope of this talk, but I'd be happy to. And there are some slides there for my papers and presentations and the library. And what we're talking about here largely is communicating sequential processes, which is from Tony Hoare. And his book is now out of publication but freely available online. And so that's the link to CSP. So thank you, and sorry for not paying attention to the time and running over.